Cars should only go as fast as can stop. Arm care that is related to power of decelerators, not the accelerators. Today's training, we train to go fast. The data tells us how fast we can go. Shoulder sphere training specifically trains for how fast you can stop, not how fast you can go. It trains for shoulder to be anchored by the rotator cuff as one functional unit to serve as a takeoff platform for the shoulder to accelerate. Shoulder sphere training is based on science, physics, and our contemporary knowledge of shoulder kinematics. Here's an example. Bauer's 90 mile per hour pitch requires a shoulder power of 40 foot-pounds per second. This is the power that is required to accelerate, but more importantly, to decelerate so as to avoid injury. It also is the power to engage the shoulder to allow acceleration. Softball pitch of over 55 miles per hour requires a power measured to be over 35 pounds per second. And again, that is the power required to go and to stop. Distance of 400 feet, 85 feet, 200 feet. Throwing distance is equal to velocity. That predicts the minimum deceleration power needed by the rotator cuff. With Jeter's jump first base throw, 150 feet, or throw from outfield to home, 400 feet. What really is the minimum velocity that is required to cover that distance? The actual throwing velocity by these athletic players can be faster, but the question is, what is the minimum velocity that is required? So this way, we can know what is the minimum rotator cuff power that is required in order for an individual to participate in that activity. We need to understand a little bit about the physics of projectile objects. Number one law is that whatever goes up must come down. So we're fighting against gravity at acceleration speed of 9.8 meters per second, or English system of 32 feet per second. We also have the known, what is the distance to be thrown. We know the launch angle of throwing. We also know that from calculations that the farthest distance with the lowest velocity tolerated take a parabolic trajectory, and the takeoff angle is at 45 degrees. By knowing these variables, we can calculate what is the minimum launch velocity required. So here's some examples. At same 45 degrees of launch angle, at 30 meters per second throw, cover distance of 90 meters. Faster, further distance, of course, 50 meters, cover the furthest. Now, if we just want to throw the same distance, different takeoff angle at 70 degrees requires a velocity of 37 meters per second. At 30-degree takeoff angle, about 32 meters per second. Now, at the same velocity of 50 meters per second, we know that the takeoff angle at 45 degrees is optimal, covers the farthest distance. These can be all calculated out by fancy calculus and equations, but spare you the pain. We just go down to the final formula derived that the range of the distance to be covered is directly related to the velocity of throw, related to the launch angle, and indirectly related to the gravity. So the minimum velocity with a takeoff angle at 45 degrees, we can calculate that as to be the square root of the distance times gravity. And the power required to throw is related to the weight of the ball, throwing velocity, and throwing distance. which translate to what is the rotator cuff power required to decelerate. So putting it all together, Jeter is 150 feet, minimum velocity of 48 miles per hour. Perhaps faster he threw it, but the minimum requirement is 48. Minimum rotator cuff power is 24 foot-pounds per second. Pitcher, minimum velocity of 30 miles per hour. Don't know if you have witnessed Dr. Fauci's starting baseball throw at the start of the baseball season. He could hardly reach home plate. So we know in order to reach home plate, a minimum velocity of 30 miles per hour must be reached. And the rotator cuff must have a power of 15 foot-pounds per second. Chapman's throw 100 miles per hour translates to 50 foot-pounds per second of power. 300 feet, outfield, 67. Between bases, 38 miles per hour, 20 foot-pounds. Softball pitcher, minimum of 25 miles per hour because the softball is a little bit heavier than baseball. Monica Abbott's world record, 77 miles per hour, translates to a 50 foot-pounds per second power. Softball between bases, 35 miles per hour. Outfield, 55 miles per hour. So these all can be calculated. That is physics. We note that the Chapman's 100 miles per hour, 50 foot-pounds, is similar to Monica Abbott. That 50 foot-pounds per second is the human limit for the power of the rotator cuff. So just for the fun, a little digression, we can talk about Patrick Mahomes' 80-yard football throw during the pro day while he was in college in 2017 at Texas Tech. Awesome 80-yard throw. So we can calculate that. The minimum launch velocity had to be 60 miles per hour. Football about 15 ounces. The power is actually 83 foot-pounds per second. He played baseball. His fastball in high school was 94 miles per hour. That translates to a power of 47 foot-pounds. So does this make sense? When he threw the football, it was at 83, but baseball was only 47. Why is that so? Yes, indeed, because the aerodynamic flight of the shape of the football can travel 2 times further during a tight spiral, so we cannot escape the laws of physics. Now, how does shoulder sphere train the power of deceleration? A little bit of understanding of the physics of rotating objects, some simple formulas. Force is equal to mass times acceleration, but because of a rotational object, this is an angular acceleration of velocity squared over the radius. We know the work is equal to the force times distance and the power and so forth. Shoulder sphere comes with an electronic power tracker. When rotating at a slow velocity, it is in green. In high velocity, it is red. So here's some calculation. At low power, under 200 rotations per minute is equivalent to the power required to throw a tennis ball about 40 feet. Or if you're playing baseball, 60 miles per hour, softball, 20 miles per hour. When you're able to get the tracker light up in red, high power, more than 400 times RPM, is equal to throwing a tennis ball 80 feet. Or if you use the larger A7 version, that prepares you to throw 90 miles per hour, or softball or 55 miles per hour. So shoulder sphere can be used as an assessment tool in addition to a training tool. If the user cannot spin the large A7 model fast enough to get a power tracker in red light for more than 3 seconds, then pretty much can forget about throwing a baseball at 90 miles per hour or a softball at 55 miles per hour. Or if a person indicates that my baseball velo is at 90, but I cannot get into red, that is a strong prediction to get injured, see you in the operating room, or be a bench warmer.